Good morning. Now, this is an important session of our module 1, that is van der Waals equation of state. So, in this session, we will learn about isotherms, critical constants, and some of the limitations of van der Waals equation of state. Okay. Now, van der Waals equation of state, we know that a real gas deviates from ideal behavior because of two wrong assumptions that we have made. The first wrong assumption was that the size of molecule of gas is negligible compared with the volume of the gas. The second one was that there was no intermolecular attraction between gas molecules. Now, these are the two wrong assumptions that we were made. But actually, uh, in actual practice at high pressure, the size of molecule is significant. That is, it is not negligible compared with the volume of gas. Also, Van der Waal, in order to overcome this wrong assumptions that is made, Van der Waal has revised these two wrong assumptions, and he has deduced a new equation of state for actual gases, and that equation is known as Van der Waals equation. Accordingly, he has made certain corrections for the pressure and volume in the equation. Okay, so hope it is clear. Now, first let us see how the correction for pressure is applied. Now, consider a molecule M1. This is a molecule M1, and it lies in the interior of the container. That is, it is attracted in all directions equally. So, the resultant force in any direction will be 0. Why? Because it lies internally in the container, and at the same time it is attracted equally in all directions. So, the net force acting on that molecule will be 0. Now, let us see another molecule M2. This one, it is lying very near to the walls of the container, so it will experience an unbalanced molecular force. At the same time, it will strike the walls of the container. Okay, with a velocity less than the velocity with which it hits the wall. Okay, now same is the case for all molecules near the boundary. Therefore, velocity and hence momentum with which the molecule hit or strike the boundary walls will get reduced. As a result, or due to this reason, the observed pressure of the gas will be less than the actual pressure. Okay. Now, this decrease in pressure actually depends on two factors. One is on the number of molecules striking unit area of the wall per second, and the number of attracting molecules per unit volume. Both these two points, or both these two factors, are proportional to density. Density means number of molecules per unit volume. C. It is proportional to density, or decrease of pressure is proportional to density square, that is proportional to 1 by V square. So, decrease of pressure can be written as A by V square, where V is the volume of gas and A is a constant of proportionality. Thus, by considering the effect of intermolecular attraction, the expression for power has been corrected. And how in the earlier case, without correction, pressure was written like P, but now after applying this correction, how we are writing is that P plus A by V square, that is, it is equal to the sum of observed pressure, that is P, and decrease of pressure, that is A by V square, due to intermolecular forces. So, this is the corrected expression for pressure, that is, instead of P we write P plus A by V square. Now, let us see the correction for volume. Okay. Now, if we consider the finite size of molecule, the free space available for movement of the molecule will be less than the volume of the vessel. Okay, now the reduction in volume can be introduced by subtracting a correction term B from the measured volume V, that is V minus B. This is a measured volume, this is a correction. So, V minus B. So, in place of V, we write V minus B. So, the correction term B is related to volume occupied by the molecules. So our ideal gas equation, which was PV equal to nRT, after including the correction term here, in place of P we write P plus A by V square, in place of V we write V minus V. This is a corrected expression for pressure and volume, and N will be taken as 1, so RT. So PV equal to nRT, that ideal equation has now become P plus A by V square, V minus B equal to RT, and that is called van der Waals equation, and here A and B are called van der Waals constants. Okay. Now our aim is to derive the expressions for critical constants, that is critical pressure PC, critical temperature TC, and critical volume VC. Okay, now as deduced before, here we write the van der Waals equation of state, that is P plus A by V square, V minus V equal to RT. From that, by rearranging the terms, you will get the expression for P as this, and that is numbered as equation number 2. Now the maximum and minimum points on the curve will be dP by dV equal to 0. So first you have to find what is the derivative of pressure with respect to volume, that is dP by dV, from this equation. So on taking the derivative, you will get the expression for dP by dV as this. That is, I am not explaining this because this is a very easy derivative. Hope you know how to take the derivative of P with respect to V, that is numerator square, denominator square, then numerator into derivative of denominator minus numerator into derivative of denominator by denominator square. By applying that formula, you will get this expression for dP by dV. So I am not deriving it now because you will get it, it is quite easy. And then RT by V minus B you will get as 2A V minus B by V cube. Okay, now next you have to substitute this expression for RT V minus B in equation 2. Then equation 2 will now become like this. Okay, now the curve passes through maximum and minimum points of the isothermals at different temperature. Now the maximum point on the curve is the critical point of gas. So at critical point, dP by dV, that is this one's derivative you are going to take, dP by dV of that equation will be equal to 0. So on rearranging, this 2 will get cancelled, this and this will get cancelled. So on rearranging, you will get this expression, and finally you will get V as 3B. Since you are concerned about critical volume, instead of V we write VC. So the expression for critical volume VC is 3B. Okay, similarly we have to obtain the expression for critical pressure PC. For that, it is obtained from equation 5 by putting, let's take equation 5. In that equation we have to put V equal to VC. Here you can see a V here, so in place of that V you have to write VC which is again equal to 3B. So in all these places of V you have to substitute 3B. Okay, then you will get the value of the critical pressure PC as A by 27 B square. So this is the expression for critical pressure. Now the last one is the expression for critical temperature TC. It is obtained by putting VC is equal to 3B and PC is equal to A by 27 B square in equation 4, which is your equation 4. See here in equation 4 you can see both V. Here in all the places of V you have to write 3B, and okay, so in that equation 4 you have to substitute, and on substituting you will finally get the value of critical temperature TC as 8A by 27 RB. So equation 6, 7, 8, that is equation 6 is BC equal to 3B, equation 7 is PC equal to A by 27 B square, and equation 8 is 8A by 27 RB. All these express critical constants in terms of van der Waals constants. Okay, van der Waals constants are A and B. Okay, PC, VC and TC are critical constants. So critical constants is expressed in terms of van der Waals constant. So that derivation is very important, or this session as a whole is very important. Okay, now we are going to obtain the reduced van der Waals equation. That is, in this case, we define P by Pc as the reduced pressure. It is represented as alpha. Then V by Vc as reduced volume, expressed as beta, and reduced temperature T by Tc expressed as gamma. Okay, so P is equal to alpha Pc, V is equal to beta Vc, and T equal to gamma Tc. So put that expression in our van der Waals equation, that is P plus A by V square, V minus B equal to RT. In that equation you have to substitute. So then that is shown in equation 9. Now after that you have to substitute the value of the critical volume, that is 3b, in this equation. Then the value of Pc, what is it, A by 27 B square in this equation, and the value of Tc, that is 8A by 27 RB in this equation. So on substituting all these values you will get and further simplification you will get this expression, that is alpha plus 3 beta square into 3 beta minus 1 is equal to 8 gamma. That is called reduced van der Waals equation, and from this you can see that it is free from the van der Waals constants A and B, so it can be applied to almost all gases. Now van der Waals isotherms, that is at fixed temperature, van der Waals equation describes the dependence of P, that is in PV plane. This dependence is represented by a family of isotherms. They are called van der Waals isotherms, and each of these van der Waals isotherms corresponds to a certain temperature. So in order to understand about their dependency, we have to consider our usual van der Waals equation, that is P plus A by V square, V minus B equal to RT. In here you are considering a V square also. Here rearranging P V square plus A equal to V minus B equal to RT V square. This is rewritten. Now you are just opening the brackets and expanding, so you will get like this. Okay, then after that you are grouping the V cube term and V square term together, and V is taken back, AB is the constant is left, and from here you are just grouping it in that is in the order of highest power of V. Okay, V cube, then V square, V, and a constant equal to 0, like that you are grouping. So if this is this is very simple. If so you just take a paper and write it down. Otherwise you can skip that sentence and you can write this slide. That is for a fixed value of P, the equation will be a third degree equation, that is V to the power 3, right? So with respect to variable V, so it is known that a cubic equation can have 1 or 3 real roots. Now the first case occurs in high temperature, that is a one root is possible only at high temperature, which is represented by the green isotherm AB in this figure. Okay, when temperature is lowered and region appears on isotherm, in this case there will be 3 roots, that is the blue isotherm EFG HIJL. Now the transition between these two types of isotherms, that is from AB to EGF EFG HIJL, occurs at a certain temperature Tk, and that temperature is called critical temperature. Okay, so this equation is very easy. If possible, it will be nice if you write this also. Okay, now limitations of van der Waals equation. First one, the value of B is not constant, but it varies with the temperature and pressure. Value of Vc is not equal to 3b, but actually it is equal to in some cases, and in other cases it is 2b. Now the value of RTC by PCVC is not equal to 8 by 3, but it is usually more than 3 for most of the gases. So this session as a whole, that is about this van der Waals equation, reduced van der Waals equation, then the relation between critical constants and van der Waals constant, then this van der Waals isotherms, limitations of van der Waals van der Waals equation, all these are very important. So please give due importance to this session while you study. Okay, so for today this is enough. Thank you.